We have seen that a vector space is a set which is closed under a vector addition and a scalar multiplication, and such that these operations satisfy a list of properties. We also saw plenty of examples of vector spaces. Next, let us define what vector subspace is, and let us look at a few examples of vector subspaces as well. So, to begin, let's start with a vector space. We say that set W is a subspace of V if W is a subset of V to begin with, and if you take any two elements in W, look at the sum of the two vectors, say W1 and W2 are the vectors in capital W, look at W1 plus W2. This makes sense because W is a subset of V and V there is a vector addition already defined. So, now look at whether W1 plus W2 is in our subset W. So, in other words, just check whether W is closed under vector addition, the vector addition which is borrowed from V. And similarly, check whether W is closed under the scalar multiplication, which is again borrowed from capital V. If both vector addition and scalar, with respect to vector addition and scalar multiplication, our W is closed, then we say that W is a subspace of V. So, let us note it, that V be a vector space. We say that W is a subspace of V if W is contained in V and if the following two conditions are satisfied. As already noted, the first one is W is closed under vector addition. I.e., if W1 and W2 are vectors in capital W, are elements in capital W. As of now, W is just some set, right. So, if W1 and W2 are in W, remember that this is contained in V, this is a subset of V. Then W1 and W2 when considered as vectors in capital V, we can add them and then see whether this is in capital W. So, note that the vector addition is borrowed from V. Not just vector addition, we also demand that W is closed under scalar multiplication. Just write MULT in short for multiplication, i.e., if C is a scalar or a real number and W is an element of capital W, small w is an element of capital W, then C times W is in capital W. And just like in the previous case, scalar multiplication from capital V. So, if these two conditions are getting satisfied, then we say that W is a subspace, and we say that W is a subspace of V. Sometimes it is also traditional to call it a vector subspace of V. All right. Let us look at some of the consequences. First consequence is that if W is a subspace of V, then W is itself a vector space with the vector addition and scalar multiplication being the ones borrowed from capital V. So let me just state it as a lemma. If W is a vector subspace, so I will slowly drop writing the word vector subspace and just write as subspace. It should mean vector subspace. If W is a subspace of a vector space V, then W is also a vector space. So I will just leave it, maybe I shouldn't leave it ambiguously, with vector addition and scalar multiplication the same as in V. So the definition itself checks for the requirement of whether vector addition and scalar multiplication is closed, or rather whether W is closed under the vector addition and scalar multiplication. So proof will immediately indicate that by definition, recall what the definition was, you will see that W is closed under, not slowly stop using the word vector addition and just call it addition and scalar multiplication. But we have a long way to go. We need to check for properties 1, 2, 3 up to 8. So let us just revisit the properties, it is written above. Let me just point out that property 1, property 2, property 1, property 2, property 5, property 6 and property 7 and even property 8. So except properties 3 and 4, every other property is automatically satisfied because it is satisfied for V. So let me just mention that, I will let you think about it as well. Note that every property except, did we say 3 and 4 or 4 and 5? So shouldn't make a mistake with that. So let me again notice it carefully. Properties 3 and 4. Every property except 3 and 4 are automatically satisfied in W, since the same is satisfied in V. Since the same is satisfied by the addition and scalar multiplication in V. So we just need to worry about properties 3 and properties 3 and 4. What was property 3? If you go back and check, property 3 stated that the vector space should necessarily have a 0 vector, a vector such that if you add any other vector to it, you get back that same vector. So if V is added to a 0 vector, we get back V. Okay, so we do not have much information about W except the fact that W is closed under vector addition, and in this case very crucially W is closed under scalar multiplication. Now by an exercise that we did in the previous session, by an exercise We know that if you consider the scalar 0 and look at the scalar multiplication of 0 with some vector w in capital W, this should end up with the 0 vector. So, if you have not done that exercise, please sit and do the exercise and convince yourself that if you multiply the scalar 0 to a vector, you get the 0 vector. Then if 0 times w is equal to the 0 vector by property 2, then by property 2 in the definition of a subspace, of a vector subspace, we have 0 times w is in capital W, because W is closed under scalar multiplication, which implies that 0 belongs to capital W. And therefore, the 0 vector of V, so let me again use colors to tell that this is the 0 vector in V, and this is also the 0 vector in V, and what we have essentially shown is that the 0 vector of V is in W and is the 0 vector of W as well. All right, so that takes care of property 3. How about property 4? Property 4 states that given any vector in capital W, there should necessarily be an additive inverse in capital W. Again, let us invoke the same exercise from the previous session. Again, note that if you have not done this, please do it. Minus 1 times W is equal to minus of W. So, this implies that again by 2, by, let me write it down in words, hence by 2 in the definition of subspace, which says that W is closed under scalar multiplication, we have minus of W is an element of capital W. So, again keep this in mind when I say that here this is the additive inverse of W in capital V. Now, it is not very surprising that the additive inverse is in capital W as well, because if you remember, one of our other exercises was to say that given any vector, the additive inverse is unique. So, we already have an additive inverse in capital V, so it better be in capital W as well, right? Otherwise, there is a potential problem of having more than one additive inverses in capital V, because the 0 is the same, right? Okay, so we have essentially proved almost all properties of properties in the definition of a vector space, and therefore we have established that capital W is a vector space as well. Let us now look at many examples of subspaces. So, the first example, so let me write it as example 1. So, consider W to be equal to the set of all x, y, comma 0 such that x and y are in capital R. Then notice that W is contained in R3, x, y, z our z coordinate is 0. That is what W is capturing. It is the set of all those points in R3 whose z coordinate is 0. Then notice for x1, y1 0 and x2, y2 0 in capital W, by borrowing the vector addition from R3, x1, y1 0 plus x2, y2 0 is equal to x1 plus x2, y1 plus y2 comma 0, which again has the z coordinate 0, which belongs to capital W. Therefore, our W is closed under the vector addition which is borrowed from R3. Similarly, let me leave it as an exercise to check that W is closed under scalar multiplication. Hence, W is a subspace of R3. Okay, let us look at another example. So, if you look at P2 of R, then it is a subset of P3 of R, right? Any degree 2 any polynomial of degree less than or equal to 2 will naturally be of degree less than or equal to 3. And if you remember, if you recall how the addition operation was defined in Pn of R, it is just the usual polynomial addition and scalar multiplication. And therefore, I will allow you to check that with the usual vector space operations P2 of R is a subspace of P3 of R. In fact, let me write down a chain of subspaces Pk of R is a subspace, in fact, is a subspace of PL of R where L is greater than or equal to K. All these are subspaces of P of R. P2 of R turns out to be just a subspace of P3 of R, right? Oh, an important thing to note is that we cannot realize R2 as a subspace of R3. R2 is not even a subset, is not a subset of R3. It is not hence a subspace of R3. We might be able to find vector subspaces of R3 which are identical to R2, as we have seen here. This is something which is identical to R2, but it is certainly not equal to R2. This is an element in R3 which has 3 coordinates. R2 is the Cartesian product of R with itself, just twice, not a subspace, not a vector subspace. Okay, let us look at more examples. Let me give numbers. Example 3. So, example 3, I would like to consider the set of all x, y, z again in R3 such that x plus y plus z is equal to 0. So, for example, 1 minus 1 0 is an element of W, or 1 0 minus 1 is an element of W. 2, 3, minus 5 is an element of W, and so on. I would like to claim that W is a subspace of R3. So we just have to check that W is closed under vector addition, which is borrowed from R3, and scalar multiplication, which is also borrowed from R3. So in order to do that, let x1, y1, z1 and x2, y2, z2 be in capital W. Then let us look at x1 plus y1 plus z1 plus x2 plus y2 plus this is what I would like to finally have. I am sorry, but what is x1, y1, z1 plus x2, y2, z2? This is equal to x1 plus x2, y1 plus y2, z1 plus z2. Now the question is, does this belong to capital W? We will check whether this belongs to capital W by checking for whether the coordinates add up to 0. So consider then x1 plus x2 plus y1 plus y2 plus z1 plus z2. This is the sum of the coordinates, but these are all real numbers which are being added up, and we know that the order, the addition is commutative, and also the order in which we add up these numbers don't matter, right. So this I will leave you to check that this is nothing but after all the commutating of elements and re-bracketing terminologies, re-bracketing the variables, we get this is equal to x2 plus y2 plus z2. I am sorry, these are not variables, the coordinates. But what do we know about x1, y1, z1? x1, y1, z1 belongs to capital W, and any vector which belongs to capital W should have its coordinates summing up to 0. That is how our W is being described, right? And therefore this is equal to the scalar 0, and the next one is also equal to the scalar 0, which is equal to 0, and we are done, and we have shown that W is closed under scalar multiplication. Well, it is quite similar if you want to show that we have just shown that the vector addition is closed. It is quite similar to show that the scalar multiplication is also closed. Check that, I do not even want to call it an exercise, check that scalar multiplication is also closed. Scalar multiplication cannot be closed, the subspace W is closed, W is closed under scalar multiplication. So it is important to write it down precisely. Next example, example 4. Consider the subspace W. So let W be equal to P even of R, where P even of R is the even polynomials, the set of all polynomials in P of R which satisfies the following property: P of minus x is also equal to P of x. Then I would like to claim that W is a vector space, vector subspace. Of course, it is a vector space as well. More precisely, it is a vector subspace of P of R. So then let me just write it down as a claim, formal claim. P even of R is a vector subspace of P of R. So let us take two such vectors and try to see whether this belongs to P even of R. So let R of x, let me call it h of x be equal to p of x plus q of x. We want h of x to be in p even of r. That will happen when h of minus x is equal to h of x. But h of minus x is equal to p of minus x plus q of minus x. But both p and q belong to p even of r, which is equal to hence p of x plus q of x. But what is this? This is exactly equal to h of x. And this implies that h also belongs to p even of r. And how about scalar multiplication? Is p even of r closed under scalar multiplication? Let c be some scalar. Let h of x be equal to c times some polynomial p of x, where c is a scalar and p of x is in p even of r. Let us check whether h is now in p even of r. So, to do that, what is h of minus x? This is nothing but c times p of minus x, but c is in p even of r. So, this is equal to c times p of x by the very definition of p even of r, which is equal to nothing but h of x. And this implies that h is in p even of r. So, we are done. This proves that we have established the claim, hence the claim is established. Because that is precisely what the definition of the subspace says, that it should be closed, it should be a subset of p of r, which is true, and that it is closed under the vector addition and scalar multiplication. So, let us look at one more example. So, consider all the diagonal matrices W to be all the diagonal matrices of size n. So, what is W? W will be i.e. matrices of the type A1 0 0 0 0 A2 0 0 0 0 dot 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 0 a n, right. This is exactly what diagonal matrices are. So, where is this sitting inside? Notice that W is sitting inside M n cross n of R. Sometimes M n cross n of R is written as M n of R. The n cross n is just abbreviated to just n if m is equal to n, right. So, I will leave it as an exercise for you to check that W is a subspace. So, maybe I should call it something else, D for diagonal matrix, it does not matter. W is a subspace of M n cross n of R. So, diagonal matrices are subspaces of M n of R. So, in particular, if you just consider diagonal matrices of size n, that is a vector space. Actually, we should be looking at the most, the first examples should have been the following. So, this maybe should be example 0, which I am putting at the end. Every vector space is a subspace of itself. It's quite straightforward because V itself is a subset of V for sure, and it's certainly closed under vector addition and scalar multiplication. So, it satisfies all the conditions for a subset being something being a vector subspace. The set W, the 0 vector space, is a subspace of V, where the 0 here is the 0 vector in the additive identity in capital V, where 0 is the additive identity. So, the second one needs a careful observation because the 0 is being added to itself here, and because 0 is the additive identity, you get back 0, and hence this is the 0 vector space we had defined. But yes, it is also realized as the subset of W here, and yes, it is a vector subspace of capital V. So, these are the first examples of subspaces I would have liked to give, but that is okay. So, any subspace of a vector space which is not the 0 vector space or the entire vector space is called a proper subspace. Any subspace of a vector space V which is not V itself or the 0 vector space is called a proper subspace. Okay, let me conclude this video by noting that, let me just write it as a lemma. The intersection of two subspaces will again be a subspace. Two subspaces of a vector space is again a subspace. Let me just give a quick proof of this. Let W1 and W2 be subspaces of V. Now, consider the intersection W1 and W1 intersected with W2. If you consider W1 intersected with W2, then clearly W1 intersected with W2 is a subspace of V. After all, W1 is a subset of V, sorry, it is a subset of V. W1 is a subset of V, W2 is a subset of V, and therefore the intersection is also a subset of V. We only need to check whether it is closed. So, let W1, W2 be in W1 intersected with W2, but both W1 and W2 are subspaces. This gives W1 comma W2 is in capital W1, and hence W1 plus W2 is in capital W1. Similarly, W1 plus W2 is also in capital W2, which implies W1 plus W2 is in capital W1 intersected with capital W2. It's very similar to check that W1 intersected with W2 is closed under scalar multiplication. So, now we have plenty of examples of vector spaces, and after developing the notion of a vector subspace, we now have a family of, so I will just conclude with an exercise for you which will give you plenty more examples of subspaces. So, let W be the set of all x, y, z such that Ax plus By plus Cz is equal to 0, where A, B and C are scalars. Prove that W is a subspace of R3. And if you prove this exercise for every scalar, every collection of scalars A, B, C, look at W corresponding to the equation Ax plus By plus Cz is equal to 0. That is going to be a subspace. So, we have many examples of subspaces. All these are vector spaces. So, yes, now we have plenty of examples of vector spaces. So, the next video we will go forward by developing the notion of what is called as a linear combination.